Good morning, everyone. My name is Jin Yiling. Thanks for giving me this opportunity to present my current work. The title of my presentation is Modeling Complex Transportation Networks. Collaborate with my supervisor, Professor Bing Jiang. At the beginning, I would like to mention that it's a review paper, and its main part is composed of three sections: topological structures, network growth, and human mobilities on transportation networks. Firstly, I will briefly introduce the background and motivation of this review paper. As the background of this presentation, it's necessary to introduce the emerging science of networks. Networks exist everywhere and at every scale in our lives. The study of networks, in the form of mathematical graph theory, is one of the fundamental pillars of discrete mathematics. The last decade has witnessed the birth of a new movement of interest and research in the study of complex networks. The most famous models in this field is small world model and scale-free model. The first one is proposed by Waltz and Strogatz in Nature in 1998, and another is studied by Barbasi and Airbolt 1 year later in Science. Subsequently, the massive and comparative analysis of networks from different fields has produced a series of unexpected and dramatic results during recent years, including statistical properties and dynamic processes on networks, from basic centrality distribution to evolution simulation and so on. Besides, based on complex network theory, some subjects also emphasized their special perspectives, such as spatial networks and the social network analysis, have developed into their own body of knowledge. As to our study object, transportation systems is an important part of a country's infrastructure system, and essential for the national economy and safety. As those pictures show, many kinds of transport systems, from aviation systems to different grounded transportation networks, are all organized as a network pattern. As a good example of complex systems, they have earned much attention from different fields and been studied from different perspectives. But to understand this topic from an overall level is not an easy task. In summary, the importance of transportation systems in modern life and the lack of a review on this topic lead us to present this review paper. Next, we will come into the main part of this paper. In this section, we will review the massive work on topological structure of transportation networks from three perspectives: their representations, basic measurements, and lastly, we will summarize some empirical analysis. As we know, the first question we need to answer before analyze the networks is how to represent a real network accurately. It's easy to generalize non-planar networks, such as aviation networks or maritime networks. But for other grounded transportation systems, we could generalize them in two different spaces: L space and P space. From the left plot, we can see in the L space, stops or stations are nodes. Two nodes are connected if they are consecutive ones on a same route. In this sense, the L space is also called space of stops or stations. P space is also called as space of transfer. All of the stops of a route can be connected between each other because a directed line can be detected between them. Due to the different generalization method, even a same network, when it's extracted in different spaces, will present totally different topological features. In the right plot, there are also two methods to generalize urban road networks, named a dual approach and a primal approach. It's much more easier to understand their difference. For the dual approach, the streets are considered as a node, while intersections are links. On the contrary, the primal approach reflects the real geometry of urban street networks, which considered the streets as links and intersections as nodes. Next, we will briefly introduce some basic measurements in complex network theory. Centrality is a fundamental concept for network topological analysis. Due to time limit, we will not explain the measurements one by one, but we would like to point out that, as the plot shows, the degree, closeness, straightness, and betweenness capture the different features of a graph, and the strength is based on a weighted network. Besides, we need more measurements to explore other topological features. We divide them into three classes: clustering, global measures, and the cellular structures. We would like to point out that the cellular structure is designed for planar network, indicating some grounded transportation networks and urban road networks. Their planarity makes them special and different from other social networks. We have mentioned at the beginning of the presentation, there have been a wide range of studies on topological features of different transportation systems. It's impossible to list all results here, but we select some typical cases for different systems. In this table, despite the worldwide aviation network, all systems are studied in both spaces, L space and P space. As we expect, they show totally different results. The average degree and clustering coefficient in P space are much higher than L space. As to the degree distribution, there is an interesting phenomenon. A scale-free distribution could never appear in the P space. Besides those results, there is also another important kind of transportation systems. We call them urban road networks. Lots of studies indicate that there is a huge heterogeneity in road networks. As this picture shows the result of Vienna, almost 20% of streets could account for 80% of traffic flow on the network. In addition, some researchers validate that less than 1% of streets, out of which the upper 20% could form the backbone of the total street system. The planarity of road network is an important feature and merits more studies. Analogical to the node degree, cell area, cell length, and form factors, and the relations between each other are also studied. Then we will enter the second section, network evolution. It's an old but still interesting subject. There are many kinds of models to simulate the growth process of networks. Firstly, we review some basic models on general network growth. Barbasi and Airbolt proposed the most famous BA model to simulate the scale-free network. The two basic principles are network growth and preferable attachment. As we mentioned above, this model, together with the small world model, is regarded as two fundamental models in complex network theory, and have attracted many attentions to make improvements on them. In the real world, new nodes could link to different nodes, and they tend to select attached nodes based on weight rather than degrees in the BA model. Here we introduce BBV model, which considered a new node can be linked to a constant number of old nodes. The ZSVG model further adopts an accelerated growth mechanism, in which the links created by the new added node also increases with time. Those two models are all weight-driven growth models. In this part, we noticed that those models do not consider the spatial effects, but real transportation systems are highly constrained by geography. Then, we should introduce some models which are more suitable for transportation networks, by considering the geographic effects. For MS model, in each time step, one new node is added with a random location in a square lattice, and the connect principle considers the distance. Here we also notice that if alpha equals to 0, it becomes the standard BA model. Another model, which we call XZ model, this model also takes into consideration the computation between geographic and topological factors by adopting different coefficients. In addition, road networks also have some special growth mechanisms. From the topological perspective, each new node can trigger the construction of a single new portion of road. We can see in the left upper plot, M is the network's closest point to both centers A and B. The road will grow to another point in order to maximally reduce the cumulative distance of A and B from the network. From the optimal perspective, there are two parameters controlling the shape of networks. A small value of P indicates the city is organized, while for large value of P, the nodes are added at random. For small w, a minimum number of roads are constructed to connect new nodes, while in the opposite case, all possible connections are added. Based on those models, researchers also developed some case studies to validate and compare those models. In this slide, we can see that empirical results of China airport networks present a good agreement with the simulation results of BBV model. Here we will not explain more about the results, but convert our focus to another topic, human mobility. Back to 2005, Barabasi said the dynamics of many social, technological, and economic phenomena are driven by individual human actions, turning the quantitative understanding of human behavior into a central question of modern science. So, our ultimate aim of exploring the topological structure and network growth is to understand the human behavior on them. To help us understand human mobility patterns, we first introduced two models, random walk and levee flight, at the beginning of this section. The left plot is a grid random walk which is generated on NetLogo. It's easy to understand the random. It means that at each time step, choosing a random direction and going with an identical step length. The level flight is a special case of random walk. At each time step, choosing a random direction and the step length obeying the power law distribution. In ecology, the levee flight is usually used to depict the search and hunting process of many animals. In this sense, we could not help wondering that how about people's behaviors? Could them also present the similar patterns? A lot of studies have been trying to answer this question. Firstly, Barabasi studied the communication of emails and found that the waiting time and the sending time all present scale-free property. This work opening the new direction of human dynamics, and people start to use different models to explain the scale-free property of human mobility. In the middle plot, a pure level flight cannot explain the model of bank bills. A super-diffusive process is needed. Besides the movement time, the distribution of mobility distance is also studied, and they all present the non-Poisson properties. Because it's still a new and hot topic, so we list some literature to help readers who are interested in this field can track the more details.